Okay, let's get started. So, you've brought us some really interesting sources today, all digging into something, well, pretty deep inside vision transformers.
That's right.
These are the models doing all the heavy lifting for computer vision now, yeah. Powering image recognition, the visual side of AI assistance, all that stuff.
Exactly. They're incredibly powerful, but, you know, like any complex system, they've got their quirks. And one that surfaced is this phenomenon people sometimes call noisy thoughts when the model's processing an image.
Noisy thoughts.
Oh.
Okay, that sounds less than ideal. What does that actually, mean for a vision transformer?
Well, it means that as the image data flows through the network, certain intermediate calculations, specific internal tokens, they get these unusually high activation values, high norms.
High norm tokens, got it. Or outliers, you mentioned.
Right, outliers is another term. And the really strange thing, based on this research, is where they tend to pop up. It's quite counterintuitive.
Ah.
Well, you'd probably guess these super active signals would be on the interesting bits of the image, right? A person's face, some intricate object.
Yeah, makes sense.
But nope. The sources show these outliers often show up in the most, well, boring parts, like a flat, uniform background, think plain sky, blank wall, that kind of thing.
Huh. So, low information, but high internal activity.
Precisely. Very weird.
That is weird. Like your brain deciding to intensely focus on a blank bit of wall instead of the actual painting. Why? Why is that a problem for the model?
Okay, so the main issue highlighted in the sources is how it messes up the attention maps. You know, these maps are our window into the model, trying to show us which parts of the input image it's focusing on for its
Right,
decision.
interpretability. If it says cat, you want to see it looking at the cat shape.
Exactly, but these high-norm outliers, they act like attention sinks, is a term I saw used.
Attention sinks.
Yeah, they just suck up a huge amount of the model's internal attention, pulling it away from the actual content and onto these noisy, meaningless spots.
Okay, so it makes the attention maps messy, harder to trust.
Totally. Much less useful for figuring out what the model's actually thinking or why it made a certain prediction.
Right. Does it just hurt our understanding, or can it actually mess with, how well the model performs tasks?
Oh, it can definitely impact performance.
Yeah.
On different downstream tasks. Because this high activity, it's not really related to useful image features, so it kind of distorts the internal picture the model builds.
Mm-hmm.
Some earlier work, which is referenced here, even suggested these outliers might be acting like some kind of, like an emergent global memory, almost like the model's trying to create internal registers on the fly.
That sounds familiar. Wasn't that linked to the researchers who first really flagged this whole issue, Darset and colleagues?
Yes, exactly.
Yeah.
That Darset paper from 2024 was really key. They clearly identified the high norm token problem and put forward that idea about it being an attempt at global information capture.
Okay, so they spotted it, had a theory why. Did they also suggest a way to fix it?
They did. And
Yeah.
it followed logically from their theory. If the model's trying to make registers, let's just give it some proper registers.
Yeah.
Their idea was to add a few special tokens, not image patches, just extra tokens to the input sequence when you first train the model.
Ah, during training.
Right. The hope was these trained register tokens would sort of absorb or handle that global information, letting the actual image tokens focus more locally. And that should clean up the attention maps.
Conceptually, okay, that tracks. Give it the tool it seems to be trying to build itself. But
Yeah.
I sense a but coming. There's a catch, isn't there?
A major catch. And this is really central to the sources you gave me. Doing it their way with trained registers means you have to retrain the entire model from the very beginning.
Oh.
Yeah, and these big VYTs, they're trained on, massive data sets. It takes huge amounts of computing power, time, money. Retraining is just, well, it's often totally impractical, especially for models already out there doing work.
Right. So, great idea, but way too expensive for most situations. We've got this problem, noisy internals messing things up, and the known fix costs a fortune.
Exactly.
And that's where this core paper you shared, Vision Transformers Don't Need Trained Registers, comes into the picture.
Precisely. Their whole mission was different. It wasn't just about observing the problem or the costly fix. They wanted to go deeper, do a more, academic investigation into what's the actual root cause.
Find the mechanism.
Find the mechanism so they could then hopefully figure out a practical fix that didn't need retraining.
Okay, let's dive into that mechanism then. How did they figure out what was actually causing these tokens to go haywire?
They were really systematic. They tracked where these high norm tokens first started appearing as the data moved through the network, layer by layer. And they saw a pattern. For different models like OpenSciLight or DynoV2, the outliers consistently spiked after going through the MLP blocks in certain layers, like maybe layer 6 for one model, layer 17 for another.
Okay, so not just anywhere, but specifically after these MLP blocks in particular layers.
Right. That pointed the finger at those MLP blocks being key players in boosting these norms.
So what's in those MLP blocks that's doing it? Did they narrow it down further?
They did, and this is where we get to a really key academic finding. They looked inside those MLP blocks and found it wasn't the whole block, but a specific, very small set of individual neurons.
Neurons, like single units.
Yeah, single neurons, a sparse set.
Right.
And what was really striking was that these specific neurons were highly active exactly when and where the outliers were forming. They called them register neurons.
Register neurons. Okay, the name suggests they have this special job. What makes them different? Why these neurons and not others?
This is where it gets super interesting and maybe challenges how we usually think about neurons in these networks. These register neurons, they weren't just firing for the single biggest outlier token in one image.
No.
No, they found these neurons consistently lit up on all the outlier positions and, importantly, across different images.
Whoa, okay, so not tied to one specific image feature then, more general.
Exactly. It strongly suggests they have this general, maybe even image-independent role related to creating this outlier effect rather than just detecting, say, a patch of blue sky.
Image independent.
True.
That's a fascinating idea. So they're not doing typical feature detection like finding edges or textures. They're doing some kind of internal network management thing.
That's the really provocative implication, yeah. And they didn't just stop at correlation. These neurons fire when outliers appear. They went for causation.
How? How do you prove causation inside a neural net like that?
They did this really cool intervention experiment.
Yeah.
They showed they could actually go into the model during its calculations, the forward pass, and directly edit the activity of only these specific register neurons.
Edit them, like manually change their value.
Kind of. They could take the high activation values these register neurons were producing and basically copy-paste them onto any token position they wanted in the sequence. Yeah. While setting those neurons' activity back to 0 everywhere else. And guess what happened?
The outliers move.
The high norm outlier behavior moved precisely to wherever they'd pasted those activations. They could literally force the outliers to appear in arbitrary locations. There's a figure in the paper, figure 1, where they make the outliers form a heart shape just by tweaking these few neurons.
Get out. They drew a heart with the model's internal noise just by messing with these, a handful of neurons.
Exactly. And crucially, they showed if you tried the same thing with random neurons, even other highly active ones, it didn't work. You couldn't just push the outliers around like that.
Wow.
So that provides really strong evidence, academically speaking, that these specific neurons, the register neurons, are the ones actually causing the high norm outliers.
Okay, that's a massive insight. Identifying these specific causal neurons, how did they then jump from that fundamental discovery to a practical, training-free solution?
Right, this is the brilliant part, the core innovation. Test time registers. The logic was basically, okay, we've proved we can control where the outliers go by fiddling with these register neurons. So why not just tell them to go somewhere harmless, like somewhere completely outside the actual image area?
Move the noise off the canvas, so to speak.
Pretty much.
Yeah.
And the key is they figured out how to do this without any retraining. It all happens at test time when you're actually using the already trained model.
Okay, walk me through that. How does it work?
So first step, you take your pre-trained vision transformer, you add one or maybe a few extra tokens to the input sequence, just blank untrained tokens. These are your test time registers.
Okay, add a dummy token.
And then second step, you need to identify the specific register neurons for that particular pre-trained model. There's a simple procedure for this outlined in the paper, basically finding neurons in those earlier layers that consistently have high average activity where outliers tend to form.
So a quick analysis finds the culprits for the model you have.
Yep. Then the third step, the intervention during the forward pass. When the model calculates the activations for those identified register neurons, instead of letting those high activations potentially mess with the image tokens later on, you intercept them. You copy those high values specifically into the slot for your new test time register token.
You redirect the signal.
Exactly. And then this is important. You zero out the activations of those register neurons for all the original image tokens.
So you capture the high norm energy in the new token and prevent it from spilling onto the actual image representation.
That's the core idea. The problematic outlier behavior gets neatly contained within this extra token, leaving the image patch representations cleaner. And again, the huge advantage. Completely training-free, post hoc. You don't touch the original model weights at all.
That is incredibly elegant and practical. You can take these giant, expensive models off the shelf, run this analysis, and then just apply this fix on the fly whenever you use them.
That's the goal, making the fix accessible for models already out there without that insane retraining cost.
So this is the big innovation. How well did it work in practice? When they tested it, what did they find?
The results they reported look really promising, actually, across several different angles. First, just looking at the attention maps, Figure 6 shows this, well, they become much, much cleaner inside the image area.
The noise is gone.
Yeah, those distracting outlier artifacts are basically gone from the image patches, which, as we said, is great for interpretability. You can actually see what the model's focusing on more clearly.
Okay, better interpretability, check. What about performance? Did fixing the noise help or hurt on standard tasks?
That's the other key result. On standard benchmarks, image classification like ImageNet, segmentation on 80E20K, depth estimation, the models with test time registers either perform the same as the original models or sometimes even slightly better.
Better. Interesting.
Yeah, check tables 2, 10, 11. And importantly, the performance was comparable to models that had been trained with registers from scratch.
So you get the clean attention and the good performance, but without the training cost. That sounds like a win-win.
Pretty much. And they saw an especially big jump in performance on tasks that really rely on those clean attention maps, like unsupervised object discovery, methods like Lost.
Right.
Using test time registers with DynaV2, which is popular for that, gave a huge boost, like 21 points in core lock score, according to Table 5. It really shows how much that outlier noise was hurting that specific task.
Wow. Did they try it on vision language models too? Like Elavi? That seems super relevant now.
It did, and that's a great application. Performance on the usual multimodal benchmarks stayed about the same, Table 6, which is good, no harm done. But the interpretability of the cross-modal attention maps, big improvement.
Cross-modal maps, you mean seeing how the language part attends to the image?
Exactly. By cleaning up the visual representation before it feeds into the language part, those attention maps showing the links between words and image regions became much clearer, much less noisy. Figure 7 has a nice example. It gives you better insight into how the VLM is connecting language and vision.
That's really cool. Just fixing that visual quirk helps understand the whole VLM better. And wasn't there also some kind of surprising result related to robustness against attacks?
Yeah, that was a really clever twist. They use their control over the register neurons in a totally different way.
How so?
Okay, so some models, like CLIP, can be tricked by typographic attacks, basically, putting misleading text into an image.
Right, I've seen those.
So the researchers thought, what if we use our ability to place outliers and deliberately shift them onto the regions of the image containing that adversarial text?
Wait, so instead of removing the noise, you aim it at the attack.
Exactly. The idea was that the high norm activity on those text patches would essentially mask or scramble the adversarial signal within the model's internal workings.
Did it work?
It worked surprisingly well. For CLIP, it drastically cut the success rate of these attacks, dropped it from over 50% down to about 7.5%, Table 7. And the really amazing part is how targeted this was. They were only messing with the activations of maybe 0.02% of the neurons.
Tiny intervention, huge effect.
Right. Compared to just, crudely blacking out 10% of the image pixels or something. It really highlights the power concentrated in these specific register neurons.
Fascinating. So, okay, it seems like these test time registers really deliver a lot of the same benefits as the trained ones, but without the cost. Did they directly compare the two approaches? Are they basically equivalent?
They did look at that comparison. The main takeaway is that, yes, they are largely comparable. Test time registers do a good job absorbing the high norms. Performance is similar. And tests like linear probing suggest they capture global info similarly. Table 1. They even found that just one test time register could often replicate the effect of having multiple trained registers. Table 8, Figure 9, which kind of reinforces the idea that their main job is just handling those big activations.
But not perfectly identical. You said largely comparable.
Right, not perfectly. There were some small performance differences here and there, and if you compared the internal representations directly, the similarity wasn't exactly 100%. So it's possible that training registers from scratch might let the model learn some other more subtle beneficial tricks beyond just handling high norms. But, for practical purposes, the test time method gets you most, if not all, of the important benefits. And the cost difference is just huge.
Yeah, makes the choice pretty clear in most cases. So stepping back, what are the bigger implications here? Beyond just a neat trick to fix VITs, what does finding these register neurons tell us about these models?
That's probably the most profound takeaway, academically speaking. It's this realization that maybe not all neurons in these deep networks are just simple feature detectors. Meaning, we usually think of neurons as responding to specific visual things, an edge, a corner, maybe a whole object part like a wheel, or even a concept like dog.
Right.
But these register neurons, they seem to be doing something different, something image independent. Their job appears to be more about managing the internal state or dynamics of the network, this outlier generation thing, rather than responding to a specific pattern in the input.
So like finding components inside the machine that aren't processing the input data directly, but are managing the machine itself.
That's a good analogy, yeah. It really opens up a new way of thinking. It suggests there might be other neurons or circuits within these networks performing these kinds of systemic, non-feature-based roles. Roles we wouldn't find just by asking what image makes this neuron fire.
That's a big shift. So future work could involve hunting for more of these special function neurons.
Absolutely. Developing ways to automatically discover other types of neurons with these more abstract, maybe system-level roles seems like a really exciting direction.
Right.
Plus, of course, applying test time registers more broadly, testing them on more models, more tasks, and maybe even exploring if we can actively use these controllable register-like tokens for something else. Could they act as a form of controllable memory? Could they help make computation more adaptive? Lots of interesting questions stemming from this.
This has been really illuminating. We started with what seemed like a glitch, these noisy thoughts, and ended up uncovering specific neurons acting in unexpected ways, leading to this elegant, practical, test-time register solution.
It really is a great example of how digging deep into how these models actually work, understanding the mechanics even at the level of weird outlier tokens, can lead directly to improvements that matter. Better interpretability, better performance, even better robustness.
So for you listening, the takeaway isn't just about vision transformers. It's that progress in AI isn't only about scale. It's also about this careful, clever detective work happening inside the models, finding ways to refine and improve them even after they're built.
And it leaves us with that really fascinating thought. If some neurons aren't just seeing features, but performing these abstract image-independent tasks, what other hidden machinery, what other unexpected functional roles are still waiting to be discovered inside these incredibly complex networks?
Always more layers to peel back. Keep digging and stay curious.
Until next time.
Keep diving deep.